Hello, this is a generalized acquisition function for preference-based reward learning. I'm Evan Ellis. This was work done with Gaurav Ghosal, Stuart Russell, Anca Dragan, and Erdem Bıyık. So Alice has a robot, Rob. Rob needs to learn what Alice wants him to do. So Rob asks Alice, I could put the mug in the cabinet, or I could put the mug by the kettle. Alice will then respond with her preference by the cabinet. And there are many features that could go into her preference, such as the final location, speed, or accuracy, and also many features that are irrelevant, such as what type of mug should I move? So Rob will then take Alice's response and update it using Bayes' rule to get a probability distribution of his belief, given all of the questions and responses that he has asked. We can then decompose this likelihood term because responses to different questions are conditionally independent. So Rob's updated belief distribution is equal to the prior multiplied by the probability of QK, which is Alice's response, given the reward function parameterized by this belief and the question that Rob asked. So in order to create these questions, Rob will have generated a large set of possible query trajectories beforehand. So Rob will then need a way of selecting which question to ask. And so he's going to do so with a querying policy that is given all of the past questions and responses so that Rob can make the most impactful and informative question to Alice. So how does Rob even select which questions to ask? The current state of the art is mutual information. Mutual information selects questions that maximize the mutual information between Alice's response and the parameterization of Rob's of the learned reward. So it's basically an entropy minimization method. So Rob gradually asks questions that minimize the entropy of his learned distribution. So when does mutual information fail? Well, mutual information will have Rob ask questions such as, which coffee cup would you prefer to have? So would you rather me put the coffee cup by the kettle or by the kettle? And remember, we're doing domain randomization, so there's only ever going to be one coffee cup at a time. And Rob might be asking questions, but not actually learning anything about the behavior, because the behavior is how he moves that mug that he's given. So even though he's reduced uncertainty in the mug color dimension, he hasn't reduced uncertainty in behavior. And I'm using color to represent induced behavior for Rob to go out and train a policy on this reward. And you can see here that even though we've learned about mug color, we actually haven't learned anything about what Rob should be doing with the mug. So mug color is irrelevant to the behavior. So were Rob to go out and train a policy, initially he might have learned to put the mug in the cabinet, and then afterwards he still learns to put the mug in the cabinet. So we've wasted a question. Our key insight here is that we care about the behavior induced by the reward, and we want to optimize an alignment metric, not the uncertainty over reward. So what do I even mean by an alignment metric? Well, for starters, an alignment metric is something that is maximized between the true reward. And it is basically a measure between two different rewards. So one example is log likelihood, similarity, which says that two rewards are aligned if they predict the same preferences over trajectories. Epic distance from Gleave et al. Says that two rewards are aligned if the Pearson correlation between their shaped rewards is 0. Row projection is another one from Balakrishnan et al., which also says that two rewards are aligned if they rank trajectories similarly, this time under the Boltzmann model. So we're going to use these, and you heard that all of them refer to ranking trajectories, and the ranking trajectories is going to ground our question answering and question asking into the real world. So the ideal solution, of course, if we knew the true reward, would just be to ask questions that maximize the alignment metric with the true reward. Of course, we do not know the true reward. However, we do know that the true reward is somewhere within our learned distribution. So we can add an outer expectation, this time over possible true rewards. The outer expectation effectively says, pretend the true reward is this reward is the true one, maximize the alignment between this and the rest of our belief distribution. And then in expectation, this is going to be a good approximation of the ideal solution. And so here I'm illustrating that we would actually ask questions about mug location, because those questions tell us about the behavior and the rankings of trajectories so Rob can ask a more informed question. We're going to focus on applications and domain transfer because it's much easier to ask questions in simulation and then deploy it in reality because you can reset the state and no harm done. So at first, we take a look at a synthetic environment where we randomly generate distributions of features from a source to a target environment. And here you can see that all of our methods, pi_row and pi_ll, beat out pi_mi, which is mutual information. And you'll also notice that they beat out every other metric at their own metric. So we're ranking them based off of log likelihood alignment and also row alignment because this is what we care about. And you'll notice that pi_ll performs best on the likelihood alignment and row performs best on the row alignment. We also run experiments in the assistive gym feeder environment where the task is to bring a spoon of food to the human's mouth. We ask questions using a Sawyer robot and then want to deploy on a Jayco robot. All of our methods outperform mutual information, and you can see as well that each alignment metric policy also performs best in maximizing that metric against the true reward. So this also has applications outside of robotics. For example, you might want to learn a reward on one distribution of text and then apply it to another. So we take comments from r/askvet, featureize them using semantic and sentiment analysis, and then learn a reward. We then apply that learned reward on comments from r/askphilosophy. Our method beats mutual information here as well, although do note that pi_ll beats pi_row even on the row projection metric, which diverges from our previous results. We theorize that this is due to the greedy nature of the optimization because it isn't perfect. So our key takeaways are that we care about learning about the behavior of the robot, not the specific parameterization, and we should use the alignment metric that we care about. In the future, we would like to extend this to gradient-based learning methods and also investigate the usefulness of different alignment metrics. Thank you.